Have you ever sat huddled beside a dying campfire on a brutally cold winter night? You instinctively hold your hands as close to the flickering flames as possible, desperately trying to trap every single wave of heat before it vanishes forever into the dark, freezing woods around you. Now, let us scale that comforting, desperate human instinct up to a cosmic level. Imagine that our campfire is not a pile of burning logs, but the sun, a colossal, roaring thermonuclear furnace pouring out unimaginable torrents of energy every second. The freezing night is the vast, silent, and endless void of our universe. Right now, at this very moment, our tiny planet Earth only manages to catch a microscopic fraction of the sun's light. The rest of it, more than 99% of our star's entire energy output, simply radiates out into empty space, completely lost in the dark. It is the cosmic equivalent of leaving a massive mansion's heaters blasting at maximum power while keeping every single door and window wide open to a blizzard. What if we could finally close those windows? What if future civilizations could build something so staggeringly massive that it wraps around our entire star, capturing every single stray photon of energy it produces? This is the mind-bending premise of the Dyson Sphere, a megastructure that represents the absolute pinnacle of cosmic engineering. It is a concept that sounds like pure science fiction, but as we look to the long-term survival of humanity, it may be the ultimate destination of our evolutionary journey. To understand how we could ever build something so monumentally huge, we have to look back at how we classify the growth of civilizations. In the 1960s, a Soviet astronomer named Nikolai Kardashev proposed a brilliant scale to measure a civilization's technological advancement based entirely on its energy consumption. He realized that progress is not just about the tools we build, but about the sheer power we can command. A Type 1 civilization is capable of harnessing all the energy available on its home planet, from the wind and tides to every ray of sunlight hitting its surface. Right now, humanity is not even on the bottom rung of this cosmic ladder. We are currently sitting at roughly 0.73, still heavily reliant on burning the fossilized remains of ancient plants. To make the leap to a Type 2 civilization, a species must master the energy output of its entire host star. This is where the visionary physicist Freeman Dyson stepped into the light. In 1960, he suggested that as a species grows, its hunger for power will inevitably outstrip its home planet's limited resources. The ultimate solution to this energy crisis would be to construct a colossal, artificial sphere of solar collectors around the star, turning the solar system into a self-sustaining powerhouse. But how do you actually build something larger than a planet? The initial classic sci-fi vision of a Dyson sphere was a literal solid hollow shell enclosing the sun. However, physics quickly shatters this dream. A solid shell of that size would be dynamically unstable. The slightest wobble or gravitational nudge from a passing asteroid would drift the shell off-center, causing it to violently collide with the star, instantly incinerating the entire structure. Furthermore, no material in the known universe has the tensile strength to withstand the immense gravitational and centrifugal forces pulling at a shell of that scale. Instead, modern physicists envision a far more practical and realistic alternative: the Dyson swarm. Picture millions or even billions of individual, independent satellites orbiting the sun in incredibly dense, coordinated patterns. These satellites would not be bulky metal boxes, but ultra-thin, miles-wide solar sails made of advanced carbon graphene, capturing sunlight and converting it into usable power. But this introduces a massive logistical nightmare. Where on Earth do we find the raw materials to construct billions of city-sized solar collectors? The answer is simple yet terrifying. We would have to systematically disassemble an entire planet. Imagine choosing a sacrificial world, like Mercury, which is incredibly rich in metals and sits right next to the sun where solar energy is most abundant. Future miners, potentially autonomous, self-replicating robotic swarms, would strip mine the planet down to its molten core, refining its minerals into ultra-thin solar collectors and launching them into orbit. Over centuries, the swarm would grow, gradually dimming the sun as a glittering web of artificial mirrors begins to choke out the starlight. This leads to the next great engineering hurdle. How do we get all that captured energy back to where we can actually use it? We cannot simply run a copper wire across millions of miles of empty space. Instead, we would have to rely on wireless power transmission on a staggering scale. The satellites would focus the harvested solar energy into ultra-concentrated, highly precise laser beams or microwave streams, shooting them across the void to massive receiving stations positioned on Earth, Mars, or giant space habitats orbiting the outer reaches of the solar system. It is a dance of unimaginable precision, choreographing billions of city-sized mirrors moving at tens of thousands of miles per hour, all while beaming lethal torrents of pure energy across the solar system without ever missing their targets. If humanity ever manages to pull off this grand cosmic construction project, our species will change in ways we can barely comprehend today. With the near-infinite energy of a Type 2 civilization, the laws of scarcity would completely dissolve. We could easily terraform Mars and Venus in a matter of years, turning cold deserts and toxic hellscapes into lush, green gardens. We could construct massive, artificial space habitats with simulated gravity, providing comfortable homes for trillions of humans. We could power colossal starships equipped with relativistic engines, allowing us to colonize neighboring star systems and spread the light of consciousness across the Milky Way. We could run planet-sized supercomputers capable of simulating entire virtual universes down to the atomic level, exploring the boundaries of consciousness itself. The Dyson Sphere is not just an energy project. It is the key that unlocks the door to a truly interstellar future, turning humanity from a fragile, single-planet species into an immortal, cosmic force. This breathtaking vision raises a haunting question. If Dyson Spheres are the inevitable destination of advanced life, why haven't we found any out there in the dark? For decades, astronomers have been scanning the night sky for signs of these cosmic megastructures. Since a Dyson Sphere captures visible starlight and uses it to do work, the laws of thermodynamics dictate that it must eventually release that energy as waste heat. To our telescopes, a fully realized Dyson Sphere would not look like a bright, shining star. Instead, it would appear as a bizarre, ghostly infrared signature. A star that has seemingly vanished from the visible spectrum but still glows warmly in the dark. We have searched millions of stars, finding intriguing anomalies like Tabby's star, which exhibited sudden, dramatic drops in brightness that briefly sparked worldwide excitement. While most of these anomalies have turned out to be passing clouds of cosmic dust, the search continues with more advanced space telescopes. Finding even a single Dyson Sphere would instantly answer our greatest existential question, proving that we are not alone, and that survival across deep cosmic time is truly possible. Ultimately, the concept of the Dyson Sphere is a testament to the boundless nature of human curiosity and ambition. We are a species that began our journey huddled in the dirt, terrified of the thunder, staring up at the distant, untouchable campfires of the gods. Now, we are designing the blueprints to build our own. We are small, fragile, and our time on this tiny blue dot is a mere breath in the context of cosmic history. Yet, we possess a relentless drive to understand, to build, and to explore. Perhaps, in some distant future, our descendants will look up at a night sky where the stars do not blink wildly in the cold void, but glow with a steady, warm, and purposeful light. A sign that we survived, that we grew, and that we finally learned how to harvest the stars.